Okay, good afternoon, everybody, and welcome back from lunch. I hope you had a lovely time, and we are just about to start this session. This first talk is by Marlon Dutra. He has over 20 years of experience in distributed systems with a strong background in infrastructure. He has also Linux systems, networking, and security. Marlon has worked for Facebook since 2012, where he's a production engineer and serves as a technical leader for the production engineering security team. Please welcome Marlon and his talk.
Hello, everyone. Can you guys hear me well? I guess. Yeah, so pretty excited to be here. This is my first time in Australia, so it's been pretty fun so far. So we're going to talk about X.509. Like, everybody uses X.509 every day, all day long. Like, whenever you access a website that's an HTTPS, whenever you read your email or you send an email, pretty much is ubiquitous, like everywhere. The thing is that even though like all of you know that, it's very likely that a lot of you don't know the power of what X.509, what we can do with X.509. So I'm going to cover a few things here that is usually not very common in everyone's life. So we're going to talk a little bit about how to build an internal CA and why, and especially how to do that programmatically with Python, and how to do like mutual authentication, how to authenticate client, and how to authenticate servers using certificates, X.509 certificates. I'm going to cover a little bit third-party apps. Unfortunately, I have only half an hour, so I can't do much. And I have a series of final tips that will be interesting. First, why should I care? Like, why am I here, and why am I talking about this? This is probably the main reason. Like, managing passwords is pretty complicated, and a lot of security vulnerabilities that we have noticed on the internet have been caused by leaked passwords or passwords committed in repos and stuff like that. But this is not the main reason. Like, there's a lot of other things that we can solve with certificates. One of them is like, you can have short-lived credentials. So I can give you a certificate that's valid for like a month or so, and so that system can only authenticate in that specific period of time. And then I need to either renew the certificate or revoke completely the access if it's a temporary thing. We can have unique identities, something that you can't have with passwords, because passwords by nature, they are shared. So they are pre-shared key material. So I don't have unique identities. So this is important for like a series of reasons, especially auditing. No shared material, like each client has its own certificate, like its own private key, its own public key, its own certificate. So nobody's sharing this key material. Sharing is very dangerous because we need to take care of data at rest, take care of data transport. So there's a lot of stuff that we need to take care of when we share things that are supposed to be secret. So if I copy a secret somewhere else, by definition, it's not a secret anymore. And mutual authentication. So usually, whenever 99% of the times when we are using HTTPS and we are talking to a SSL-enabled website, we only have the client authenticating the server. So if I'm talking to Facebook or I'm talking to Google, my browser is making sure that it's talking to Google and Facebook or whatever else. But we don't have the other way in authentication. So X.509 can do that as well, and I'm going to talk about that. So when I'm using certificates, when I need to have a certificate, this is always the workflow that we follow. So I generate a private key material in my host. That private key material should never, ever leave that host. And I'll talk a little bit more about that later. And based on that private key material, I can create a certificate request that we also call like CSR. That certificate request is signed by the private key. So that's the only way that the other side can make sure that I possess the private key, even though the other side, that's the certificate authority, doesn't have the private key in hands. But it has a way to verify that I possess the private key because of the signature. And then that certificate request is sent to the CA, to the certificate authority. Might be something internal, that's what I cover here. Might be something public, like VeriSign or DigiCert or Equifax or like many others. And then the CA does their diligent work to verify that you in fact on that domain, and then they issue a certificate. A certificate is basically your public key, that's the counterpart of your private key, signed by the CA's private key. And then some extra metadata, that's your domain, it's valid for a year, or something like that. But essentially, the cryptographic part, the most important part, is that you have your public key signed by the CA's private key. so that anywhere else in the world that has access to the CA's public key, that's like public knowledge, can verify that that CA with possess of the CA's private key sign your certificate. As I said before, private keys should never, ever move. So you generate a private key, it would be always there in the systems that you generate. So, of course, if you're building an internal CA, the first thing that you need to do is actually to create the key pair and to create a self-signed certificate. Why do we need an internal CA? So there is like many reasons. So with an internal CA, we can issue like a shit ton of certificates. Like we can have like certificates for every system, for every client, for every service or people, or basically like anything where you might need to identify a client. If we need certificate like public certificate, we need to pay for each one of them, and they usually cost like a lot of money. So in order of a few $100s every year per certificate, that's too expensive. That's one of the reasons. The other reason is security. When you have your private CA, you control your destiny. Like you control how secure that is. Whereas if you have a public CA, you are just as secure as the public CA is. Most of the public CAs, of course, they're very secure. But if you can control your destiny, it's usually better if you can do that well. So that's how we create. So usually when we're creating a CA, we don't make that programmatically because we do that like every couple of years or so. It doesn't make sense to have like something very sophisticated to create a CA. So I have a few commands here. So the first command is like openssl rec, where I create a new request basically. And then I create a new key. We strongly recommend not to use RSA 1024 anymore. So at least 2048 or more. Maybe for a CA, even like 4096. Yeah, we save the key in the ca.key and the request. So I'm not going to send that request to another CA because this is a self-signed CA, so I can sign my own request. So the second command actually does that. So there is this dash self-sign where I'm creating a CA that's signed by its own private key. That's fine. All the root CAs in the world are exactly that. And my CA in that specific example, it's valid for 25 years. So usually we suggest something like pretty large, but even though we should be rotating that ever so well. Yeah, I have an alias that I have on my laptop, so I can inspect CAs like very quickly without typing this entire command. So if I inspect my CA, I create like a small CA as an example. So I have all this information, the subject. So I have country, state, PyCon, Australia. It's valid from July to like 2041. And anyway, the cipher that I use and how it was signed. And then like there's a lot of information when you run that command. A lot of stuff doesn't really matter because it's the cryptographic part, but the metadata is pretty important. So I'm not here to talk about shell scripts or openssl command. I'm here to talk about how to do that with Python. That's what matters for us here. There's a lot of libraries for that. Most of them are built on top of openssl. Using openssl directly is pretty annoying. The API is super old. It's not object-oriented, so it's pretty annoying to use. But fortunately, most of these libraries, these bindings on top of openssl, they have like an object representation of certificates and requests. There's many of those. I personally like the Python cryptography the most. Most of the stuff at Facebook are built in cryptography. But anyway, this is a personal choice. M2Crypto is very nice as well. The site is cryptography.io, and you can use pip to install. Just make sure that you install the openssl libraries before you run pip. So you need that to compile because it's, as I said, it's built on top of that. So why should we handle certificates programmatically? So the main reason is that we can have something like fully automated without human intervention. So if you have like a very small setup, a small infrastructure, it may be okay to have like a few shell scripts where you can sign your certificates, or you can do some manual human validation. But if you have a larger infrastructure, it really doesn't make sense anymore. So you need to have something that can operate on its own. So it's beyond the scope of this talk to talk about how to do that super securely. But the thing is that when you have a programmatic CA and it's well implemented, you can issue lots of certificates everywhere and without human intervention. That's pretty important. So this is just an example of how I can read an existing certificate. So I created that CA before. using the openssl command line. And here with code, I'm interpreting the certificate. The certificate is a very standard format. It's based on ASN1. Most likely will be base 64 encoded. That's called PAM certificates. They are base 64 encoded. So I have all the imports. So I load the file, and then I have this X.509.load PAM certificate. And I use the default backend, that's openssl. And then I have an object, that's a certificate. And then that object has a lot of attributes, has a lot of methods. So one of them is the common name, the CN. The CN is the most important thing in every certificate. It's like the title of the identification of the certificate. So that's super important. For SSL certificates for websites, it's usually the domain name. For client certificates, it's whatever you want. So in that case, here is the CA, so the common name is just the name. And I have dates, like not valid before, not valid after. Interesting is that I have actually Python objects out of that. There's a lot more information that I can have in a certificate, and I would probably spend like half an hour talking about this. So let's go back to the workflow that I mentioned before. So I create a private key, I create a certificate request that's signed by my private key, and I send that to a CA. How can I do that programmatically? So if I build my own CA, I need to build my CA client as well, because I need to run the client everywhere. So my client would look something like this. Lots of imports. I'm using all of them in the next page. So I want to focus on that. So I have private key. The first thing that we need to always do is to create a private key. As I said, that private key should be there and should not move. So RSA, you can use elliptic curve. It's probably better, but anyway, for this example, I'm using RSA 2048. Public exponent is usually 64K, and the backend is openssl. So the private key will be an object that represents my private key, and I'm going to use that like, so scrolling down. I have a builder. So a builder is basically certificate signing request builder is my CSR. I'm doing pretty much what openssl recommend does. So I have a builder, and then I have the subject. So my subject has a CN, it has a country name, it has a state. It can have a lot of other attributes. So I'm just mentioning like 4 of those here, but I can have more things. I can have extensions. So this particular extension is called basic constraints. That says that this CA will not be used as a CA. This certificate request will not be used as a CA. So when I get a certificate back from the CA, that certificate will not be used to sign other certificates. So this is pretty important. Sometimes you might want a sub-CA, that's fine. You can have all sorts of different extensions. There's a lot of newer extensions in the X.509 standard these days. So I use the builder. So you notice the pattern is not very clear, so I need to reassign the builder all the time. That's because the builder object is immutable, so we can't change it. So whenever you call builder.subjectName or builder.addExtension, that actually returns a new builder object. That seems very strange. But anyway, it's the way it's been implemented, so there's probably a reason for that. Scrolling down. So I have the request. So I have the builder, and from the builder, I have the request. As I mentioned before, the request is signed by my private key. So that's what I do in the first block there. So builder.sign, I have my private key. I'm going to sign using the hash SHA-256. Please don't sign anything with SHA-1 anymore. It's going to be deprecated December of this year. So I think all modern browsers, as of January 1st next year, will not accept SHA-1 certificates anymore. So sign everything with at least SHA-256 or more. SHA-256 is very, very secure. So I don't think it's going to be a problem in the next several years. And then save everything. So I have a CSR, that's the certificate request. Let's save that the disk, and I have the key. Obviously, I need to save that, otherwise my certificate will be invalid without the key. So in that particular example here, I'm writing the key with no encryption. So most of the cases where I'm using this programmatically, I don't want to have a password, because otherwise someone needs to go there and type the password. So I send this to the CA. So usually, most of the times, like in the real world, I don't write down the CSR to disk. I just send the CSR straight via wire to the CA using like REST API or Thrift or something like that. In the Facebook case, we always use Thrift. So I move that CSR to the CA side, and now the CA needs to verify and then sign it to generate a proper certificate. All the imports, I'm going to use everything. So I open the CSR. In that particular example, I'm open from the file system. In the real world, I'm most likely open from a REST request or from a Thrift API. So I open the CA, open ca.crt. I transform that in an object. I open the CA key. because I need the key to sign the certificate. And then, yeah, it's serialized, so I need to deserialize. It has no password because it's programmatic. Scrolling down, again, the builder object. So this time it's not a certificate builder. It's not a certificate request builder. It's actually the certificate builder because this is the CA. The CA builds certificates. So it is the same thing. I need to reassign everything all the time because the objects are immutable. And I have the subject name. In that example, I'm just copying the subject that the CSR sent to me. In the real world, you never do that because you can't just trust what the CSR asks you. So you need to do some sort of like programmatic validation. The issuer name is always your CA. So that's by definition, the issuer name will always be the CA.subject, even in the real world. Not valid before, not valid after, how long your certificate is good for. One pro tip here. So in that particular example here, I'm starting with right now. Like I would not recommend doing that. Usually start like an hour before, 2 hours before, because there's a lot of clock skew in the internet. So we can't assume that everyone will have the clock like pretty well aligned. So usually at Facebook, I think we start at least an hour before, even though we have NTP everywhere, and we know that our clocks are supposedly aligned. But anyway, it's a good practice to start like a little bit before. So in that case here, it's valid for 7 days. How long it should be valid for really depends on the case. There's no silver bullet here. The certificate public key must be the public key that came from the CSR. That's by definition. Like it can't be different. Otherwise, you are building an invalid certificate. The serial number, in that case, I'm just using UID to make it random. Random is fine. As long as it's unique, it's fine. Some people do it sequential. We used to do sequential at Facebook. But it was very hard for us to coordinate because we have the CA distributed in like hundreds of servers. So it was very complicated to coordinate uniqueness. So now we just moved to random. It's much easier. And we have a seed to make sure that we won't have collisions. Extensions. So in that case, I'm just iterating the extensions from the CSR, and I'm adding those extensions to the certificate. Of course, you never do that in the real life, so you need to do some sort of validation before actually doing that. So scrolling down, the last thing, and probably the most important, is actually sign the certificate. So builder.sign, the private key that I'm signing the certificate with is obviously the CA. The hash that I'm using is SHA-256. As I said, don't use SHA-1 anymore. And I'm writing that certificate to disk, but in the real world, you would most likely be returning that certificate in your API output somehow. So that's the very basic workflow that you have from a CA client and then a CA service. So in the real world, you would probably have some more validations and authentication and stuff. So once you have certificates, like you have your CA, your services have certificates, your clients have certificates, how can we use them? Like, how can we make this whole thing useful? So before diving down a little bit more in authentication, I want to talk a little bit about AAA. So authentication, authorization, and accounting. So authentication it needs to answer one simple question. Who are you? And are you who you claim you are? That's the whole thing. The authentication, by definition, is not an evidence that you have access to something. It's just authentication. I am Marlon Dutra, blah, 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 etc. So that doesn't mean, by definition, that I can do anything. So the next step, that's probably the important thing in terms of business logic. That's the authorization. So once you have a very strong authentication, and that I'm secure, I'm very confident that you know who you claim you are, then I can move to authorization. Then I can say, can Marlon do what it's trying to do? And that's the whole thing about authorization. There is no authorization if we don't have a strong authentication. If I can impersonate each other here like very quickly, there is no good authorization in the world that will solve any kind of problem here. And accounting is keeping track of what happened. This is like super important. So moving on. So SSL server. If I want to build an SSL server in Python, that's pretty much how I do it. This is Python 3.5, because I'm pretty sure that nobody uses Python 2 anymore. Hopefully that's the case. Anyway, Python 3.5 has changed a little bit how this works. And so yeah, a couple imports. So we create something that we call a context. So this comes from openssl. So I have this context that's for client authentication. And this is a server code. So my server code, you have this certificate and this key. And the CA that my server trusts is the ca.crt. And the verify mode is required. So that says that whenever I have a new connection, I, as a server, will require that the other side, the client, provides a certificate. Everything else here is just standard socket boilerplate. There's nothing new here. So I'm listening to this port. So scrolling down, more code, I do the accept. Of course, that would be in a while loop, in a thread pool, or something like that. And then I have this wrap socket. That's where the authentication happens. So the accept actually does the TCP three-way handshake. So if the accept didn't throw an exception, that means that you have a TCP connection established. And then we have the wrap socket. That's where the SSL handshake happens, like all the client hello, server hello, and et cetera, usually 2 round trips. So that's where the authentication happens. If we pass that call without raising an exception, that means that both the client authenticate the server and the server authenticate the client. So the client provides a certificate that's signed by the CA that I trust, and the certificate is not expired. So the interesting thing is that in the third line, I can actually get the certificate that the client provided, and I can load an object using X.509, and I can interpret that certificate. So in that case, I'm just printing the CN as I showed before. Once I have the certificate and the authentication is done, I can actually do all sorts of authorization. So now I know that Marlon is connected. He's my client. Then I do all my authorization code the way that I want. Like, can Marlon do that? And then I just close the socket. This command is very interesting. Everybody has that. It's an openssl as client. I can use it's like a telnet, but with SSL support. And I can pass certificate and client key for that. So you can use that command against anything. And then it will show you the certificate and everything. Most likely, in the vast majority of the cases, you are not writing socket code. Because there's a lot of good projects out there that can do that for you. So Apache, for example, I can configure my Apache server to do that for me, so I don't need to worry about that in Python itself. So I can configure Apache, pretty much the language is obviously different, but it's expressing the same thing. So verify client require, verify depth 1, that means that I only trust certificates signed by that CA and not sub-certificate. And I might want that for some reason, but this particular example I don't. So where is the certificate that I trust? So everything needs to be signed by that certificate. And then in Python, if I use CGI or SSGI or anything, I have that available in an environment variable. Some different systems like WSGI might be a little bit different. But anyways, all of them will expose the client certificate somehow to you. And then you can use the X.509 cryptography module to transform that in an object, and then you can do all the authorization logics. The only thing that you are offloading here is the authentication. You are not offloading the authorization. Authorization is a business thing, and then you need to do it yourself. If you want to do it with MySQL, for example, you can configure MySQL to accept client certificates as well. So the main configuration in the section MySQL that's the main session for the server. I can say, I trust that CA, and as a server, this is my certificate, this is my key, and I can create internal users in MySQL with the create user command that requires subject something, and whatever the subject is. And then whenever the client presents that certificate, the client will automatically become that internal user. No passwords at all here. On the client side, if I'm using Python, I can do that as well. So I can use MySQL DB, and instead of have user and password, I have this dictionary where I pass the CA that I trust, because the client also needs to authenticate the server, and then my own client certificate and my private key. And then I connect to any host, and then SSL, no passwords at all. So this is way, way more secure than ever using passwords. A few final tips. Unique serial numbers, I mentioned that. It's important for several reasons. To keep track of all the certificates that you issued, so this is pretty important. So usually when you write your own CA, have some sort of secure logging, like append on logging. Try to log to different systems like syslog, whatever. So you keep track of all the certificates that you are issuing. So if you ever have an incident or something, you know what is going on, most likely. And also for revocation. So you might have a revocation infrastructure, and then you must have unique serial numbers to revocate certificate. Short-lived certificates, this is pretty important. If you have a programmatic CA, there is no reason to issue very long certificates. How short? It really depends. At Facebook, it varies. For user certificates, we usually do 24 hours. For service certificates, 1 day or so. Host certificates, we usually do a couple weeks. It really depends. There's no right answer here. rotate your CA every so often and have a process to do that. The main reason to have a process and to make sure the process works is that what if your CA gets compromised? Like, what if it leaks? If your CA leaks, you are totally screwed. You need to rotate your CA immediately, and then you need to pretty much revoke everything that you have ever signed. If you have a process and you rotate your CA like every year, or every 6 months, or whatever, you know how to do that, and you've been exercising that process. So whenever the necessity arises, you know how to do it. If you don't have a process, you have a very hard time to rotate your CA. Don't trust public CAs in your internal systems, because there's a lot of public CAs. So if you look at your laptop trusts a lot of CAs. So if you trust public CAs, basically you are saying that you are trusting your level, your entire level of trust is as good as the weakest CA that you trust. So if someone compromises any of those CAs and then can sign a certificate with the information that you need to trick your authentication authorization systems, they gain your system. So just trust your internal things. There's no reason to trust public stuff. Never move private keys around. Whenever you move, you need to control very precisely like all the residuals of the movement. So when you're moving using SCP, you need to take care because you might be using temporary directories, you might be forgetting keys here and there, or keys might be available in memory even though you don't know. There's a lot of things that can happen when you're moving keys around that you were not aware. So just don't do it. There's no reason to do it. You have certificate requests and have entire very standard workflows, so you don't need to do it. Be very aggressive to eliminate user passwords. That's probably the main reason that I'm here talking to you guys about this. So user passwords are super complicated to maintain programmatically. So there's no, anyway, pretty much everything that's modern these days support X.509 mutual authentication, Postgres, MySQL, etc. Lots of stuff do that. And on the server side, Nginx, HAProxy, Apache, probably Django, a lot of stuff. And the last, and probably the most important things, you need to be serious about protecting your CA. If your CA leaks, everything else falls apart. So be very serious about that. We're hiring, if you are passionate about this kind of stuff, or anything around software engineering, infrastructure, etc., come talk to us. I have a couple of friends here. We're like 6 engineers here, so feel free to reach out to us and talk about Facebook in general or any cool stuff that you might like. I have a few prospects here if you want to know a little bit more about production engineering. I think we have a few minutes for questions, I guess. Do we have?
Just a couple of minutes.
Yeah.
So thank you very much, Marlon.
Yeah, sure.
Okay.
Thanks for the talk. Just following up on that final point, be serious about protecting your CA. How do you bootstrap this? Like, how do you authenticate someone who's calling your CA trying to get that initial certificate?
That's a very good question. So at Facebook, for example, like this is just an example. You can do like in several different ways. We have three kinds of certificates: user, hosts, and services. For user, the source of trust is my password and Kerberos authentication. So all laptops, they are a member of an AD domain. So when I unlock it, my laptop runs kinit in the background, so that fetches a Kerberos ticket. And then when I SSH to my dev server, that's my Bastion host, that Kerberos certificate gets moved, and then using that and single sign-on, I can request an X.509 certificate that belongs to me. For host, is based on our provisioning system. So our provisioning system is maintained by the security parts maintained by the security team. So whenever we provision a new server, the provisioning system will sign a token, and the server will build the private key, the CSR, and it will send the CSR and the token to the CA. And the CA validates the token. Now, did the provisioning system sign this? And then it gives back a certificate. On the services side, we have a scheduler that pretty much orchestrates all the allocation of services across Facebook. We trust the scheduler. So the scheduler is also maintained by the security team. So it's the same thing. When we start a new job in servers, we have like an RPC call called like start task or something like that. And that has a signed token by the scheduler. And then it's the same thing. The task creates its private key, its CSR, sends the CSR to the CA with the token, and the CA validates the token. So that's very Facebook specific. Of course, for different business, we might have different ways to do that. But anyway, you need to have a source of trust. because the trust needs to start somewhere. Otherwise, you'll have always the chicken and egg problem. So that's how we do it. If it's the best way to do it, for us, it's been. I'm not sure that it would be the best way to do for other people.
Thank you. I think one quick final question. Was it? Yes. Sorry, just before I go, for those who, before you flee the room, if you have lost anything, please see registration.
Thanks. Just wanted to ask about the error handling in cryptography, if it's just kind of passing OpenSSL errors back and they're like equally as cryptic, or if it's a little bit better.
To catch, it's basically everything is based on, everything raises exceptions. So your code needs to be like try except and everything. So it's different than using OpenSSL directly, that you need to be checking the return of everything. That's pretty annoying, but it's very Pythonic, the way they built on top of OpenSSL, which is pretty good. So most of our code is actually try this, and that, and catch all sorts of exceptions, and then do something on top of that. That's how it works. Yeah.
Would everyone please thank Marlon?
Thanks.